Hello everybody, my name is Arseni, and today we're going to be speaking about graph convolutional neural networks. Unfortunately, at the time of recording, it is dark in my room and my wife is sleeping, so there's going to be no light and hence no webcam. So I just drew a schematic picture of myself, so that you have a feeling of presence in the frame. It's arguably better looking than I am, so I think that works. Alright, so what are graph convolutional neural networks and what are we going to be talking about today? So, as you could guess, in order to understand graph convolutional neural networks, by the way, I'm going to refer to them as GCNs in the future because I'm having trouble pronouncing it every time. So, GCNs. You need to understand graphs, you need to understand convolutions, and you need to understand neural networks. So when it comes to neural networks, I'm not gonna give any refresher on that. We're not gonna go through it. So I assume that you know that, and if you don't, it's probably best to pause the video right now and go online, find some kind of tutorial so that you are comfortable with this idea and at least familiar, because otherwise it's gonna be difficult to follow this tutorial. So when it comes to convolutions, I assume that you heard about it and that you're familiar with the notion of a convolutional neural network, but I'm gonna give a quick reminder, refresher, so that we're on the same page, because I need this knowledge to be fresh in your mind and readily available when we're speaking about GCNs. And lastly, we are gonna talk about graphs. I'm going to define what I mean by a graph, and so if you never heard about graphs, you should be fairly okay throughout the tutorial. And so the plan is actually going to be like that. We're first going to cover graphs just briefly, introduce the notion of a graph. We can speak about how could a graph be applied to a real-world problem, how could we represent a real-world problem in a graph form. Then we're going to speak about convolutional neural networks and how they are related to graphs. And through that, it's going to be easier for us to understand what a graph convolutional neural network is and why it is called this way. After that, we're going to look at a small implementation of a graph convolutional neural network in PyTorch to see how that actually works in practice. A little bit of a disclaimer, I must say that we're not going to be actually looking into latest and greatest practical applications of convolutional neural networks. We're also not going to implement one ourselves. We're going to look at one of the openly available implementations of simple GCNs, just to understand how the ideas that we discussed can be translated into the code. I decided to do it this way so that we could focus on understanding and, unfortunately, combining deep understanding of what graph convolutional networks are doing with a thorough implementation. It would have required just a little bit too much time, so one thing had to go, and the practical side of things gave way in this case. All right, with that being said, let's jump into it and let's begin speaking about graphs. So in general terms, the graph is a collection of nodes and edges between them. So graphs could be different, and there could be different types of graphs. So for example, there are directed graphs. So let's call them directed. And this is the case when the edges, that is the connections between nodes, are directed. So this connection is different from this connection. So this one is different from this one. And if the graph is directed, all connections are directed. All edges are directed. The graph could also be undirected. So in this case, if there is a connection from node A to node B, they're saying that there is a connection between a node A and a node B is the same as saying that there is a connection between a node B and the node A. So there's no one-sided connections. Graphs could also be weighted or unweighted. In a weighted graph, there's a certain number associated with every edge. So different edges could have different numbers, of course. So something like that could be an example of a weighted graph. In an unweighted graph, all edges have the same weight, or we could say that they have no weight, but you get the idea. There are no numbers associated with every specific edge. More generally, we could say that some graphs could have features associated with either the nodes or the edges. So for example, the weighted graph is an example of a graph where there's only one feature associated with every edge and no features associated with the nodes. So the feature in this case is this single weight. At the same time, sometimes it can be helpful to have more than one number associated, or rather more than one feature associated with an edge. So for example, if nodes represent cities, so very non-creative names for the cities, but nevertheless. So if edges represent cities, and let's say the edge corresponds to the fact that there is a airline, or there's a flight available between those two cities, and let's say the edge could have a length. The length could be very natural. For example, the time of an average flight between these two cities. So t equals to, or t bar equals to, I don't know, 6 hours. But at the same time, it could also be that there's another feature that we are interested in, and that would be the price. And price could be equal to, I don't know, 100. Well, for 6 hours, it should be pretty far. So let's say $300. So this is an example where every edge would have more than one feature. So every edge would have the average flight time and the average price of a ticket. So this could be like 3 hours, and the price would be, let's say, 150. If there is no edge between a certain pair of nodes, what that could mean is that this is maybe a very small city, let's call it Z, and there's just nothing that flies into the city. And if we're planning for the optimal route, there is no optimal route there because, unfortunately, there's no way to get there. Similarly, you could imagine that we could also associate some features with nodes themselves. So in case of cities, it's again, it could be population of the city, 6 million, for example. And for our lonely node Z, the population could be 300 people who don't know how to get out of there and who don't know how to get into their town if they leave it somehow. So yeah, you see the idea. So in general, the list of different types of graphs, it goes on and on. I just want you to have a general idea of what kinds of graphs there are. And right now we're going to look at a couple of examples to just see how something in the real world can be represented as a graph. So this was one example, but we're going to cover a few more just so that you have a better intuition of what is going on. All right, so we've introduced what a graph is, and now I want you to pay full attention because I think this is one of the most important moments of the whole workshop. Because we're going to talk about different problems, real world problems where you could apply machine learning, and we're going to try to identify which one of those can be represented in a graph form. And so essentially, even if you forget everything else I say, I would still be happy with the outcomes of this workshop, as long as you can identify when a problem you're facing can be represented in a graph form. Because if you do remember that, then you can always Google this workshop or any other material. So you can always Google everything as long as you identify a moment when Googling is necessary. So I hope you're motivated, and let's look at a few examples of graphs and real-world problems that can be represented as graphs. All right, so the way I want to do that is I'm gonna vaguely describe 4 problems to you, and I want you to guess whether or not this problem has to do anything with graphs, whether it could be meaningfully represented in a graph form, or not. So the first problem is as follows. We have a class of a bunch of students, and we're interested in answering the following questions. We're given any two students. We want to say to be able to say whether or not the first student likes the second student. The second problem is that of drug discovery. So given any molecule, we would like to predict what would happen if we give it to a person who's having a flu. So there are three possible outcomes. The first one is the person is going to die. Second one is that nothing is going to happen. So the person is still going to have a flu. I don't know. He's crying probably. And the last one is the person is going to be completely healed. This is slightly unrealistic and simplified, but that is the problem setting. If you think that this problem setting is a little too extreme, you could instead imagine that we're just classifying whether or not the molecule would have any positive effect on an individual. The third problem is about predicting used car prices. So you have a car, you have some characteristics of this car, and you want to predict the price for this car on like a reasonable or an average price for this car on the aftermarket. So that is the problem setting. And the last problem, the fourth problem, is as follows. It is the good old image classification. So we have an image of something, and we would like to classify what is on this image. Is it, well, to keep it simple, let's imagine that it's a good old MNIST problem. So we have 10 possible classes corresponding to 10 different digits. So ideally, when our algorithm sees this digit, we would like to output that it's a 7, and if we show our algorithm something like this, we would like the output to be 0. So here we have it, the 4 problems. I actually encourage you to take a piece of paper right now and write down your answers, because I wonder what your intuitions are, and it just so happens that if you don't do that, then retrospectively, it's actually not that easy to evaluate whether or not your intuitions were correct. All right. So 3, 2, 1, I'm gonna reveal the answer right now. All right, so I hope that you have answers in your mind. And I also hope that apart from just saying yes or no, like first problem can be represented, second cannot be represented, etc., that you also have an idea of how you can represent it as a graph and what kind of graph that would be. So I didn't say that initially, so if you need another 3 seconds, I'm gonna count down right now. Pause the video if you need to. So 3, 2, 1, 0, and now I'm actually going to reveal the answer. All right, so let's take a look at that. So first of all, problem number 1. It can be represented in a graph form, and I think that's the most natural way to represent it. So you could imagine that we would have different students as nodes. Edges would be directed, and they would represent whether or not a certain student likes this other student. So student A likes student B. If that is the case, then there's a directed edge between the student A to the student B. At the same time, you could also imagine that that could be a weighted graph. So for example, a weight of 0.5 would represent, a very mild liking, just the absence of animosity towards somebody, while the edge of 1,000 would represent that this is actually that the node D is the love of C's life. So if you are the node D, then predicting whether or not this edge is there and whether or not the value of this edge is positive becomes the matter of very, very crucial practical importance, as you can imagine. And so in order to make this prediction more accurate, we could also imagine that apart from just edges and values associated with edges, we could add some features to the nodes. Let's say there's a gender, there's age, there's I don't know, eye color, and stuff like that associated with every node. And there could also be some additional features associated with edges. Let's say, how far are those two students sitting from each other in the classroom? And so maybe if we identify that this is a very important feature, the node C is gonna try to sit close to the node D. So this is, let's make this C, and let's make this node D. So you see that C is strategically placing himself near the node D. All right, so hopefully that is clear enough. And hopefully you all agree that this problem can be represented in a graph form. And even though this example may seem like a toy example, something not very realistic or not very serious, things could get very serious very quickly. And if, for example, instead of predicting who likes whom, we could predict the outcome of an election or of whether or not a certain bill passes in Senate. So if you model the relationships between senators, or actually I'm very bad when it comes to knowing the political system in the United States, but you could imagine that there would be groups of people who are connected, and there are going to be features, and one of the features could be whether or not a certain senator is going to vote yes on a certain bill. And so, as you could imagine, this decision and this feature would partially depend on what is the feature of what is the value of this feature in the nodes that are connected to the senator. And this could be very complicated, and the stakes of predicting this correctly or incorrectly could be very high. So while in general I like those toy examples, I hope that you are going to be able to generalize from those toy situations to serious real-life examples that you may encounter in the course of your career. And in general, I think that simple examples are best for this purpose because they don't introduce too much detail, and it's easier to see the analogy between the simplified scenario and a real-life scenario than it is when you have one complicated real-life scenario and then you have another real-life scenario, because the details tend to get in the way, and sometimes it's not as easy to see the analogy. All right, let's move on and talk about drug discovery. So drug discovery could also be modeled using graphs. So in this case, we're having a different situation. Every specific drug is an instance of a graph. So in this case, we have one graph, and we want to predict a certain feature of a certain element of this graph. While in case of drug discovery, as you could imagine, different nodes would correspond to different atoms, and the whole graph would correspond to one molecule, and we want to say something about this molecule. So in this case, we're classifying graphs, while in this case, we are classifying elements of the graph. This dichotomy actually has a name. So this mode, when we're classifying different graphs, is called a batch mode. While in this case, when we're classifying, when we're predicting something about the element of a given graph, this is called a single mode. And I hope you notice the the sad irony. So yeah, given the name of the problem, the things don't look too good for the node C, but who knows? The things could still work out for them. Now, the next problem, problem 3, actually should be colored differently, because I personally don't see a natural way to represent this problem in a graph form. So I must note that this is not all set in stone, and sometimes it's better to represent it in a graph form, sometimes it's not. But in this case, we're usually speaking about a specific entity. We're looking at a car. Right, we have some kind of car, and we have a list of characteristics of this car. So I don't know, year, I don't know, miles per gallon, brand, etc. Right, so if we have those characteristics, essentially everything is very isolated. So we look at this case and we're predicting a certain number associated with this case, in this problem, this number is the price, right? So the reason why graphs don't seem very appropriate of a model for this case is that essentially every element is very isolated. So you could construct a graph of those cars, let's say like this. Every car would have a bunch of features, miles per gallon, year, brand, etc., and the associated feature that we want to predict, its price. But as long as there's no reasonable structure between those cars, using graphs for this problem doesn't seem very reasonable, because really the graphs can benefit from learning the structure and learning how the structure informs different features. At the same time, if there's no meaningful structure, we can represent this as a graph neural network, but it would be completely redundant and not useful. So that being said, if, for example, we don't have the brand name in the feature, and instead this brand name is implicitly represented in the similarities between cars. So let's say all cars of the same brand are connected, and this is true for every brand. So in this case, if we were to get the car information in this, vague, the car brand information in this vague implicit way, using graphs for modeling this problem would be very reasonable. So again, my answers to those questions, they are not set in stone. So in certain situations, maybe this problem would not have meaningful connectivity, but would have a lot of features about every individual, and you would actually not need, and maybe you won't need a graph neural network for this problem, although it seems most natural to model it using graphs. And similarly, maybe in some variations of this problem setting, it would be appropriate to use graphs to model it. But my intuition is that in the most standard form, in the most natural form, this problem is not very well suited for modeling with graphs. All right, so now let's cover the last case. And in this case, the answer is actually yes. This can be meaningfully represented as a graph, although it may seem somewhat surprising. So in general, we tend to not think about image classification as having something to do with graphs. But that is only a surface level interpretation. So in order to understand what does this problem have to do with graphs, we are going to review how we usually classify images with convolutional neural networks, and this is our opportunity to review the convolutional neural networks, which is something I promised to do in the beginning of the workshop. And after that, we're going to see how we could apply graphs to this problem, and we're going to see the analogy, and we're also going to understand why the graph convolutional neural networks are called the way they are called. So let's review how do we deal with images, how do we deal with image classification in general. So an image is usually just an array of pixels, a grid of pixels. For now, let's assume that the image is black and white, so there's only one channel, and that every pixel can be either on or off. So in this case, yeah, we're gonna have something like that represent any given image. Trying to be fairly careful here so that our visualization is pretty. I think I failed already, but that happens. That is life. Such is life. Well, in any case, so this is how an image looks to a computer, roughly speaking, right? Some pixels are on, and I'm gonna shade them down. So these are the pixels that are activated, and everything else is not activated. So this is my feeble attempt to draw a digit 7. It doesn't quite look like one, but I hope you'll forgive me that. So let's say we're looking at a digit 7, even though it doesn't look like it. So how do usual, like a regular neural network, approach it? So they would look at every pixel value in the image. They would multiply this value with a certain weight associated with this specific pixel and get a vector of activations. Then they would apply some kind of non-linearity. They would then apply another set of weight to those non-linearities, and it's going to proceed until we get to the output layer, which predicts the class 1 out of 10. So a regular, non-convolutional, fully connected neural network would look everywhere. Every pixel is going to have a weight associated with it. So that is the main idea. I promise that there's going to be no review of neural networks, and I think I lied a little bit, but that was not intentional. And I hope that since the review was very brief, that lie is forgivable. So how does it differ from the case of convolutional neural networks? Well, the difference is actually pretty substantial and pretty fundamental. So a convolutional neural network, instead of looking at every possible pixel and associating unique weight with this pixel, it would have something that is called a convolution or a filter. And what this filter is doing is the following. So the filter would look at a certain window, and it would have a weight associated with every element in this window. So in this case, we have a 3x3 filter. So this is our filter. It looks at every value of every pixel in this window. It multiplies the value of the pixel by the weight associated with this position in the window, and it sums up the results, right? So let's say this purple is positive weights, red could be negative weights, or let's say thin is negative or near zero weights, and we're getting a value. We're getting a value by computing this filter in this first position, right? So let's represent this value. Let's draw this value as this little square. So what would happen next? After we computed this value with this filter in this position, we're going to shift the filter to a neighboring position, or we could jump over a position. Let's say we shifted it a little bit, and now next time we apply this filter, the weights, so this weight is going to be the same as this one. I'm just using a different color so that it's easier to see what exactly is going on. So now we're using the same weights, but on a different position, and it's still 3x3. So we're applying these weights, and we're getting the next pixel in a way. We're getting the next pixel computed by this filter. So if we proceed this way, shifting this filter and computing those pixels, we are gonna get another picture. But this is going to be a filter picture, and that is what the process of that is how the convolutional neural network functions. So there's only one subtlety behind that, and the subtlety is that the filters, the picture that I drew, it only considers one channel. The real picture would actually have not only one, like on every step of this process, there's going to be more than one layer. So the original picture would have usually 3 layers, and those 3 layers, or to be more precise, it would have 3 channels, and those 3 channels would correspond to red, green, and blue light respectively. And then instead of having just one filter that we applied like that, and with which we constructed this new layer activation, we would have more than one filter with different weights, and they would construct more than one channel on the next step. So this is a technical detail, and it's actually not that important. It's just if you are already familiar with convolutional neural networks, if you're wondering where are the different filters, where are the different channels, yeah, they're under the hood or swept under the carpet. That being said, I hope that this visualization helps you to remember the general idea behind convolutional neural networks. And if you never heard about them, I hope it makes it at least somewhat intuitive. In the case the previous visualization was not making it intuitive, I made it slightly better by color coding the activations received by applying this filter in different positions. So if that doesn't help to make convolutional neural networks intuitive, then nothing will. Just kidding. In fact, this is again just a very, very brief recap of what convolutional neural networks do. It's not a proper introduction to them. So if you're confused, consider checking out some tutorial that goes in more depth into what convolutional neural networks are doing. So what is important for us is that why actually convolutional neural networks are doing so well on images. So it is just the fact of life that convolutional neural networks are the best when it comes to image classification, and we would like to understand why. And so the reason why they're so good is that they exploit the connectivity structure that exists between different elements of the picture. So convolutional neural networks share the weights. So essentially they treat any patch of connected pixels the same way, because they know that there's something important about pixels that are near to each other. So in other words, convolutional neural networks exploit the 2D structure of the images, and we managed to encode this intuition about the fact that the image is a 2D grid by saying that, use this filter in every possible position. It would make sense. In other words, we could say that we're telling the convolutional, oh my god, I'm just gonna say CNN, which is the acronym for convolutional neural networks. So CNNs, they know that there's something about those pixels, that they are close together, and this is not a coincidence. How can we use this intuition about the proximity of pixels being important and transform this problem of image classification into a graph-related problem? So again, convolutional neural networks, CNNs, exploit the local connectivity between pixels. They exploit the fact that the pixels that are close to each other, this pixel is close to this pixel, but this pixel is not close to that one, so we're not gonna treat them within the same filter. So they exploit this 2D structure. How can we generalize this approach and transform the problem of image classification into something that has to do with graphs? So if you've been listening carefully up to this point, maybe you can guess. So I'm gonna give you 3, 2, 1, 0. I'm gonna reveal the answer right now. So to understand that, imagine that we're again looking at a small image that is represented as usual as pixels and their activations. And now the thing is, we could instead think of it as a graph. So imagine that all pixels, kind of started floating apart, and now they're just floating in space without being arranged as a grid. And so now suddenly pixels turn into nodes of our graph network. And nodes are going to be connected. So and essentially we could do it in a simple way. We could say that, nodes are connected if the pixels are neighboring each other. But it seems that kind of loses some of the information. It's not that we just know that this pixel is connected to this one and it is not connected to this one. We also know that this pixel is much closer to this one when compared to this one. So instead of just saying that there's a node that there's an edge between two pixel nodes if the pixels are neighboring, we could say that all pixels are going to be connected, but the weight of the connection would depend on how close the pixels are. Let's say we have a very high weight of 10 for pixels that are neighboring each other. We could have a weight of 8 for pixels that are no further than 2 pixels apart, etc., all the way to 1 for pixels that are actually very far apart. These numbers are completely random, and this is not something you have to. This is definitely not set in stone. Those weights could be different. They could also be learned. But the important thing is that from this static grid representation, we're transforming our problem into this representation that is a graph with pixels floating around in space and being connected to each other with different weights depending on how close they are in the actual grid. The features of the nodes in the network could still be, however, just the good old activations as we had before. So now we know how to represent an image as a graph, and so an image classification problem becomes analogous or equivalent to the problem of classifying a graph, which is, if you recall, in this case, the batch mode, because every graph is a thing that needs to be classified. We're not classifying the values of individual pixels. So now, in order to gain the deep insight of this lecture, and in order to understand what the graph convolutional neural networks are doing, we need to extend the analogy from just transforming the problem into transforming the solutions. So we know that the solution for this problem is a convolutional neural network that would look at this picture, construct the second layer of activations using filters as we discussed here. All right, so let's say after filtering, we're getting a new image. Let's say the filter was small and the size of the image decreased, because we won't always have the same size of the image every time. So like in this case, if the filter size is 2 by 2, we're gonna activate in this position, then we're gonna activate in this position, activate this filter in this position, and lastly here. And so we're gonna have 4 possible activations of the filter. So after transforming this initial image, the black one, with the filter using the convolution, we're gonna end up with 4 pixels. But the key thing is that we're transforming something that looks like an image, that is a grid of pixels, we're transforming it into something else that also looks like an image, in a sense of being a grid of pixels with some activations. So that is what happened after we applied the convolution, right? And then we're gonna take this something that looks like an image and pass it through another layer of convolutions to get yet another layer, etc., etc. So what is important in this case is that we're transforming the images into something that looks like images, and we're doing it repeatedly. So we've learned how to transform the image classification problem into a graph classification problem. And now we want to transform this approach as well. So what was happening is that the convolutions were kind of accumulating information about neighboring pixels and combining this information using the filter into this new pixel. So this new pixel that is obtained by applying the filter to this 2 by 2 region, it contains some information about all the neighbors, about these 2 nodes that are all neighbors of each other. So analogous idea for a graph would be to transform this graph into a new graph, such that every node would somehow accumulate the information, would somehow represent the information accumulated from all the neighbors of the node in the original graph that is the the father or the ancestor of this node, the pre-image of this node in the transformed graph. So again, we're taking this graph, we're transforming it somehow in such a way that every node somehow accumulates all the information from neighboring nodes, and this way we're getting a new graph that can be again transformed further and further using analogous operations. So I hope you see how this is analogous to this. And that is what graph convolutional neural networks are doing. So think about it for a minute or two, pause the video if you need to. I hope it kind of sinks in, and I hope it is kind of interesting. The idea is kind of beautiful and interesting, and after that, we're gonna see how we could implement something like that in Python. Before we look at the PyTorch implementation of GCNs, however, we need to speak a little bit more about what is exactly the formalism that we're going to use. Because so far we discussed the intuition, but we just need to write the formulas and define the problem that we're working with. So we have images, right? And we need to somehow transform them into graphs using the principles that we discussed before. So this is the image of a number 7, which is the number for this workshop for some reason. Right, so we're constructing a graph based on this image. So every pixel becomes a node. We just have a collection of nodes, and they're not ordered anymore. The idea of this being a grid is forgotten. We're not using this idea anymore. So we pick some arbitrary ordering over the pixels, and this is important, that the fact that the graph assumes that there is no natural order on the nodes. So we somehow unroll the image. Let's say if it's 26 by 26, so this thing is going to be 26 by 26 long. So we have this, the nodes and their features. In this case, the features of the nodes are just their activations. And on top of that, we have what is called an adjacency matrix, which is a very common way to represent what a graph is. So if we have 3 nodes, or any number of nodes, the adjacency matrix just says which nodes are connected to which other nodes. So let's say the matrix has, 1, 2, 3, 4, 5. Let's say the matrix has 5 rows, then it is going to have 5 columns as well, because it is always square. And if there's a 1 in any given position, so if there's a 1 on an intersection between the row I and the column j, it means that in the graph, the node I is connected to the node j. And as an exercise, as a quick exercise, you could pause the video for a second and tell me, how would an adjacency matrix look for the case of directed graphs? Or rather, how would adjacency matrices look for undirected graphs? What is something special about any adjacency matrix for any undirected graph? So I'm going to count from 3 to 0, 3, 2, 1, 0, and I'm going to give you the answer. So recall, in an undirected graph, if there is an edge between the node A and B, it is the same as saying that there's an edge between node B and A. So there's either a connection or not. So there cannot be a connection from A to B, but no connection from B to A. This would be a directed graph. So in the case of a matrix, what it tells us about the adjacency matrix for undirected graphs is simply that it is symmetric. So if the node I is connected to the node J, it means that the node J, well, in this case it's 1 and 2, so let's not confuse ourselves. It means that the node 2 is connected to node 1. So I hope that you have some background on matrices, but I also hope that this is intuitive, even without a course on linear algebra. Essentially, the matrix is going to be symmetric across the diagonal. So in more general terms, this is the feature description of every node. So in our example with binary images, every node only has one feature, but generally that could be different. So for example, if we have not black and white, but instead RGB images, every node would have 3 features corresponding to red, blue, and green channels. So first of all, we have H, which would be the matrix of a size n by d, where n number of nodes and d is number of input features for every node. So this is one element that we have. Then on top of that, we have the adjacency matrix. And what we want to compute some function of h and a that would give us a new graph. So essentially a new matrix of the size n times f, where n is still the number of nodes, and f this time is the number of output features. So just to reiterate and make sure that we're on the same page. So the problem can be formulated as follows. We have this matrix H of the features of different nodes. We have the matrix A, the adjacency structure that essentially describes the graph. And on one step of application of a graph convolutional neural network, we're computing, given the current node features, we're outputting the next layer of node features. So we're transforming the graphs as we describe here. So in most general form, it is just some function of the node features and the adjacency matrix. And to indicate the idea that this is one step or like one layer of propagation, we could add an index to this h. So if h is the node representation or node features on the layer L, then node features on the layer L plus 1 can be obtained in this way. So this formula describes the general structure of GCNs. When we speak about a specific GCN model, it's like, there are many different types of convolutional neural networks. Similarly, there are many different types of graph convolutional neural networks. So in order to specify a specific one, we need to explicitly give this function f. What is this function? And essentially different functions f would define different types of GCNs. And as a simple example, just to show what kind of function that could be, just to clarify, it's not the latest and greatest model, but it is a simple and elegant model. We're going to look at the model that is defined as follows. So the node features on the next level, or the graph representation on the next level, if you like, is going to be equal the sigmoid activation function. So this is a commonly used nonlinearity. People who do neural networks just like to pass things through nonlinearities because otherwise everything becomes equivalent to one layer oftentimes. So the sigmoid nonlinearity applied element-wise to the following expression. So it is the weights on the layer L times, this is a matrix product, the graph representation, the node features on the layer L, and times the adjacency matrix. The adjacency matrix, by the way, does not change from layer to layer because the graph connectivity structure remains the same. We're just transforming the nodes, but we are keeping the number of nodes constant. We may change the number of features, so we may change how many features do we want the node to have, every node to have. That is allowed. So we're gonna unwrap this expression right now, so don't worry if you don't understand it fully. Also feel free to pause the video if you want to try to meditate on it and try to understand it on your own. Don't meditate for too long, however, before I fix a typo, because, you know, meditation on expressions with typos could have very, very bad mental health side effects. So, yep. Now there are no typos. And we could think about what this expression means. Why would we choose such a function? So in order to understand that, let's actually visualize the different matrices that we have. So we have the matrix A. It is of size n by n, where n is the number of nodes. It is multiplied by the matrix H, and H has a side n by f, where f is the number of features, or number of input features. And this is multiplied by the matrix W, where it is of size f, where f is the number of input features, times D, where D is the number of output features. So what are different nodes in this case? So different nodes in our current representation occupy different rows of this matrix H. So this is our current representation of the graph. It's feature representation. So this row is, you know, the feature 1 for the node 1. This is feature 2 for the node 1. This is feature 3 for the node 1, etc. So what happens when we multiply this matrix with a weight matrix? First of all, let's figure that out. So in this case, when we're multiplying two matrices, or a feature matrix by a weight matrix, it's useful to think of a weight matrix as being composed of a bunch of stacked column vectors. So when we multiply a vector by a column from the right, what happens is essentially we are taking every column from here and summing those columns with the weights taken from this vector. So if W was just one column vector, what we would have done when we multiply the matrix H by this one column vector, we would have taken the first column of H, multiplied it, every element in it, by this first element in this weight vector. Then we would have taken the second column, multiplied it by the second element, etc., etc. So, and afterwards we would have summed up all those weighted columns to get just one new column. Since we have stacked columns here, essentially what happens is that we repeat this procedure for every column in this matrix, and we stack the results. If you never saw this interpretation, it is actually extremely interesting, and I encourage you to take a look into, maybe review a little bit of linear algebra, because this, when you think of matrix multiplication in this way, it becomes way more intuitive why that thing would be used in machine learning. So as a result of this expression, what we're getting is a new, well, let's write an equal sign. For now, the A matrix remains unchanged. And here what we're getting is a new matrix, I don't know, let's call it H prime. It's going to be of a size of n times d. And every column in this matrix is a combination of features from this matrix, or is a combination of columns from this matrix. So essentially, what we're doing here is we're taking a feature matrix and we're reweighting the features, combining, linearly getting new features from the previous ones. So this is the step that is happening in regular neural networks. So this is completely not new. This is just what we always do when we're training feed-forward neural networks. If there was no a matrix here, or if it were an identity, this would have described a regular feed-forward neural network. So this should be familiar. I said before that I want to review neural networks, and here I am, but well, nothing I can do at this point. We did review a little bit. So what happens on the next step? How do we combine this adjacency matrix with this transformed feature matrix? Well, when we combine them, it's useful to use another interpretation of matrix multiplication. This time, we should interpret this A and N matrix as being a bunch of rows stacked together. So when you multiply a matrix by a row on the by a row vector on the left, or from the left, what happens is you're essentially stacking the rows of this matrix with the coefficients given from this row. So what that means is that when we perform this matrix multiplication, what we're going to get in the first row is going to be obtained by taking all of these all of those rows and summing them together as a linear combination with the coefficients taken from the first row of this matrix. So what that means in turn, since this matrix is an adjacency matrix, it means that we're gonna obtain a representation for the first node by combining the representations of all the nodes that are connected to this node, weighting those representations proportionally to how strongly they are connected, because that is what the elements in this adjacency matrix are giving us. And so finally, in this way, we are obtaining our output matrix, which is HL plus 1, which is going to be of size n by d. So hopefully this procedure is clear. I would be happy to clarify it. You could ask me on Discord or anywhere else. So, and that concludes our discussion, in a sense that is the implementation. That is why we picked this type of function here. So because this function does the following: it essentially first reweights the node features by combining different features together and recombining them, reweighting them. So we construct new features from old features, and then we construct new. So that happens when we multiply those two. After that, when we multiply the result of this operation by this adjacency matrix, we're recombining the nodes by pulling the information from the neighboring nodes, and that is the key idea that we introduced. So this is what we wanted to do, and that is how we formalize that mathematically. So the cool thing about it is that this model can actually do different things. It's not only for classification problems. So first of all, let's figure out how would you even do classification in this case. So if you want to classify if you have a single case prediction type of problem, so when you want to predict something about a specific node, when you're given only one graph, what you can do is maybe you don't have good feature representations, and you could train the feature representations. So that is one way to use this model. So in our image classification example, we have the initial input representation for every node, right? We know whether the pixel is on or off. So that is the feature representation for the inputs. At the same time, in some other cases, some problem could give you the connectivity between the nodes. Let's say in this class student liking kind of example, it could be that we're not actually given any features about the students, but we are only given the connectivity structure between them. And we may want to infer the latent features of those students that would help us to represent and replicate this connectivity structure. We can do that too. So in this case, we would actually train the representation as opposed to providing it right away. If we want to do classification on every specific node, we could take the last layer representation and then just pass it through some kind of some simple classifier to obtain the final prediction. So for every node, we would have a representation, and then we just pass it, as we usually do when we work with neural networks. We would pass it through some one layer, one fully connected layer, and we obtain a prediction for every node. At the same time, if you want to predict something on a graph level, let's say you predicted the features for n nodes. So you have this big matrix HL, where L is the last layer of your GCN, but you're not interested in predicting anything about every specific row, which corresponds to different nodes. In the pixel example, different rows would correspond to the features, to the transformed features of every specific pixel in the input image. You want to predict something about the whole graph. So in this case, you could also do different things. You can, the simplest way to make a prediction, you could just collapse everything across the rows. So you could compute one pooled representation. So that would have the same amount of features as the final, the same amount of features as every node, but there's only going to be one row. So from this, we went to that. Alternatively, you could actually unroll this matrix and construct one huge representation. That would work if you always have the same number of nodes in the graph. So generally, there are many tricks. What I wanted to say here is that different problems may require adjusting this model in a specific way. But what I want you to remember from that is that this GCN model is very general, and you could tweak it and tune it in different ways, and it would give you solutions to very different problems, from unsupervised learning to semi-supervised learning and supervised learning in a single case or in the batch case. Yeah, it can do a lot of stuff, and that's pretty amazing. So what we're going to do now is that we're going to take a quick look at how this kind of model can be implemented in PyTorch. Again, we're not going to implement it ourselves, and we're almost at the end of this workshop. It is pretty lengthy and pretty heavy on a lot of thought-provoking material, so I don't want to overload you. I'm afraid I already may have. So what I want to show is that the implementation is actually very simple. When we have the ideas written down, what we write in PyTorch is just a direct translation of what we wrote on paper, with a little bit of jumping around to make sure that everything is separated into functions, etc., etc. So let's look at the implementation provided by the authors of one of the pioneer papers on graph convolutional neural networks. So I think it's a very, very elegant implementation, and there's also great blog posts by the same person covering the material. Part of this tutorial was based on it, so I'll definitely put a link into the description. So let's look at how the code is structured. So the key thing is this graph convolution class. So it is a layer, and let's say what is going on in this layer. So this GC layer is the building block of everything that we were doing, and this is corresponding to this transition that we were speaking about earlier. So one layer performs this operation. And so as long as we could stack those layers and combine them, we have the network essentially implemented. We just need to repeat this layer a couple of times, and we have the model. So now let's come back to it. So this is just the initialization of the layer. We have the input and output features. The bias is something that we haven't covered. It's not really important, so let's just ignore it. I mean, it can be important in certain cases, but it doesn't change the fundamentally what is going on. If you would like to see in the formula, we're just going to add a bias somewhere here or somewhere else. Sometimes it is useful, but not crucial. Sometimes, I mean, sometimes it's crucial for performance, but it's not crucial for understanding of what is going on. Then we're initializing the weights. So this parameter function makes it so that PyTorch kind of tracks, keeps track of this tensor, and when you optimize the model, this is going to be optimized. At the same time, input and output features, the number of features are just integers, and PyTorch would know that, and it would not try to pass the gradient into an integer, which would be very unfortunate type of behavior. So those are just technicalities. What is important, however, here we are initializing the parameters. That is all great. What is important is that sometimes the implementation, the initialization matters. So you could start with random weights that would be normal. You could start with random weights that are uniform. And even though it doesn't sound like something interesting, sometimes it is very important to figure out which weight initialization works for a model best. Let's not focus too much on this, however, and move forward into the forward function. So the forward function gets the input, which is the current representation for the graph features, and the adjacency matrix. So everything is exactly how we discussed it before. The most interesting part is happening. So the bias part we did not fully cover, but what about this? So take a look at what is going on here and try to remember from the lecture what does it correspond to. And so MM is matrix multiplication. SPMM stands for sparse matrix multiplication. So in general, the graphs could be sparse, so only a few nodes are connected to other nodes. So it makes sense to represent the adjacency matrix as a sparse matrix. But this is a technicality that doesn't really affect our general understanding. So what is important here is that we're first multiplying the input by the weights. And this is exactly the same thing that we wrote down in formulas here. So first we're multiplying this. And the authors call this variable support. I'm actually not 100% sure where this terminology is coming from. This has something to do with linear algebra, but I don't quite remember which exact what exactly they mean there when they were naming the variables. What is important is that this variable is later multiplied by the adjacency matrix, and the order of variables is important. So we're multiplying by the weights from the right, and we're multiplying the result by the adjacency matrix from the left, and we're just returning that. And that is all. We're just we're gonna apply the non-linearity to that somewhere later, because graph convolutional layer is essentially in this code. Using that layer, we're computing this part that is inside of this non-linearity, and then we're gonna add the non-linearity in some other pieces of code that would actually take this layer and stack it a few times, apply non-linearities, etc., etc. So I'm not gonna go into covering the training code, just because it is essentially standard. So as soon as we implement this graph convolutional layer, the training procedure and everything else becomes the same as, like you would write it the same way as you would for a regular neural network. The only difference is that you're going to have to keep track of the adjacency matrix. But that should not be that much of an issue, because the adjacency matrix does not change throughout the course of training. So you would just pass it through to the forward function of your network, and that's pretty much it. Implementing it in an efficient way so that the batches are accounted for properly, that there's proper vectorization, that may be a little trickier. And in general, I think if you want to apply GCNs in practice, it is best to use one of the available libraries. And there are quite a few of them. Because probably your implementation would not be as efficient as what people did already. So it's been quite a long workshop. So what we covered today, we spoke about how you could represent problems as graphs, and we found out that many machine learning problems are graph structured. We also discussed how GCNs extend the convolutional neural networks by generalizing this idea of pooling information locally based on local connectivity to a more abstract idea of combining information from different nodes in the graph that are connected to the node of interest. Then we found out that GCNs are extremely flexible and they can be adapted to a variety of problems. So the same model that we covered here, with just a little bit of tweaking or different training regimes, with no tweaking at all, can solve very different types of problems. And the main thing that I would like to highlight, the main conclusion that I want you to draw, is that I want you to be afraid of missing a chance to apply graph convolutional neural networks in your work. So what I mean by that is that now that you know how you could interpret a machine learning problem in terms of a graph, how you could represent your problem in a graph-based way, maybe some of the problems you're working on can be represented this way. So think about it, keep that in mind. It's a powerful method, and if your problem has a very natural interpretation in terms of graphs, GCNs could be a wonderful way for you to improve the results that you're currently getting. Or maybe you could think of new problems that you were maybe worried or afraid to tackle before, and now you know that actually if a problem looks complicated, it looks like some huge graph structure, maybe you have a tool for it. So I encourage you to think about it, to keep that in mind, that there's a great method that you should try applying. And when that happens, if you're not sure how exactly to apply that, you could reach out. You could reach out to Google to see how to apply the GCNs in your specific case. You could also reach out to me or any other mentors in the AI club. I'm sure I will be happy to help, and I'm sure everybody else will be happy to help as well. So we didn't go into many specific implementations. We didn't go into the latest and greatest implementations for sure. I just want you to know when this tool can be applied, and if you need to apply it, I hope you have strong intuitions and that you'll be able to figure out the details when you need that. So that being said, thank you so much for your attention, for watching this workshop. I hope that was helpful, and all the best, and see you around soon.